Srimati Vijayalakshmi Sinha, Mr. B.R. Kumar, distinguished members of the audience. I deem it a great honor to deliver this Sardar Patel Memorial Lecture. I would like to in particular thank Prasad Bharati for extending me this privilege. No person who has closely followed India's struggle for freedom and her consolidation later into a democratic republic can miss to note the crucial role of Sardar Patel. Indeed, utterance of his very name has been a source of inspiration for our young men and women. Although hailing from a typical middle-class peasant family in Nadia of Gujarat state, he became a symbol for our nation's unity and strength, self-reliance and self-respect, firmness and efficiency. Among his many contributions as the first Deputy Prime Minister and Home Minister of independent India, two stand out distinctly: his vision for a secure, strong India and his emphasis on efficient administration. The firmness and efficiency with which he integrated over 500 princely states into our republic bestowed him the laurel of the Iron Man of India. Remarkable achievements of India, such as the installation of democratic polity, its institutionalization and sustenance in face of the toughest challenges, owe a great deal to the ideals represented by illustrious personalities like Sardar Patel. India's endeavors in science and technology, and particularly its role in enhancing the economic, social, and environmental security, have deep significance to the nation-building task initiated by Sardar Patel. In today's globally interconnected world, where there is fierce competition among nations, the role of science and technology is even more crucial. However, the gains go only to those who excel, who can build institutions that promote innovative use of technology. India's endeavors in space are an example where such a holistic approach to development is adopted. Our vision for space, as unfolded by Dr. Vikram Sarabhai, was to make India second to none in the development and use of space technology to leapfrog the process of development. The uniqueness of this vision was that he saw new opportunities in space for a developing country, a large country like India, barely within 3 years of the launch of the first Sputnik. And this was in contrast to the common perception that the spectacular space feats of the early era were nothing more than an extension of the Cold War rivalry. More explicitly, in the vantage point of space, he perceived possible solutions to issues of national development, particularly bringing education to the doorsteps of masses and generating timely and precise information about weather and natural resources in a way that could help our farmers and policy makers to take better decisions. His intuitive mind saw that space is a community resource, having outreach to all and capable of serving without distinction between rich and the poor, and transcending the barriers of knowledge, literacy, and any form of social or geographical imbalances. Over the past 4 decades, the Indian space program has turned this vision into reality. What is most significant is that we have not only developed capabilities to meet national needs, but also achieved a position of excellence by global standards. Let me say a few words about the beginnings. India's space efforts began in a modest way near a sleepy village of Tumba near Thiruvananthapuram, close to which the Earth's magnetic equator is situated. I will recall here that when this facility had to be set up, Dr. Sarabhai went around, looked where work could be started immediately without the necessity of building buildings and so on, and he found that there is a church around. He went and talked to the priest in this church and said whether I can start the Indian space program in this place. The priest was so happy and so thrilled that he said that he will immediately vacate this place and he will find an alternate location for his church so that the Indian space program can start. I think it augured well for our space program. And it is something even today we cherish. We have this church which have been turned into a kind of a temple, a kind of a shrine, where people visit and look at the history of the evolution of the Indian space program. For those of you who had not had a chance to visit this place, I invite you to see that place, a historic location with a very, very interesting history behind it. A sounding rocket launch facility was established to enable scientists to study the unique phenomena associated with the upper atmosphere in this region. This is also of great interest to the global scientific community. The first rocket, which took off in 1963 from Tumba facility, marked an important milestone for Indian space program. It was a small rocket, weighing just over 20 kilograms and reaching a height of 200 kilometers. Kindly see this 20 kilogram against the massive 400 ton that was the GSLV. In 1968, this facility was dedicated to the United Nations to enable the international scientific community to conduct research from this unique place. While scientific quest was the immediate aim of such an activity, this step was crucial in developing the nucleus of culture where large group of persons in diverse activities learn to work together for accomplishing a single objective. This was facilitated by establishing in the vicinity of Tumba's rocket launching station a space science and technology center with objective to develop expertise in aerospace engineering, manufacture of atmospheric sounding rockets, and a modest satellite launcher. The aim was to produce men and women who acquire the capability to do front-ranking research. There was also clear understanding that engaging in advanced fields of research would inevitably lead to collaborative relationships at international level and an ability to deal with peers, establishing mutuality which can sustain such relationships. These initial endeavors enabled the development of a strong ethos for self reliance and paved way for an operational space program for this country. What are the steps we take to reach this preeminence? Our space program evolved through three major phases. The first phase related to the initiation of activities with the objective of proof of concept evaluation, and that was followed by the experimental phase that demonstrated an end-to-end capability. This finally led to the operational phase with systems providing regular services. In the initiation phase, one of the primary tasks was the evaluation of the efficacy of space systems as an alternative to conventional terrestrial systems, or to look at them as complementary or supplementary to conventional approaches. The pioneering satellite television experiment was such a step to evaluate the efficacy of a satellite based broadcasting system with a vast outreach to provide developmental communications and literacy. It was a unique sociological experiment of its kind anywhere in the world, involving 2,400 villages spread over 6 states of the country, covering nearly 200,000 people, and it used the American satellite ATSF satellite. Actually, this in sense was the dream of the father of the communication satellites idea, Sir Arthur Clarke. He thought that if and when 50 years back, or even more than that, if and when this idea of a geosynchronous satellite could be realized, one should have immense potential to deal with problems of education and literacy in developing countries. And when, for the first time, a consortium of international operators of the space system for communication, the Intelsat, was inaugurated way back, decades back, in the room of the President of the United States, he made one mention that today, even as we sign this major agreement, a very important experiment is being conceptualized across another continent, that is India, where this very capability is planned to bring education to the doorsteps of houses in each and every place in India. So that was highly prophetic, and today what we see in the use of space, this is one of the major things that have happened in this country. Similar studies were done for evaluating efficacy of imageries obtained from space for quantifying the natural resource status and to observe changes in them. In all these studies relating to the initiation phase, use of foreign space systems, configuring the ground system to suit the national needs and conditions, and working closely with potential user community were the essence of the related efforts. This phase also witnessed the development of the first satellite launch vehicle, the SLV-3, with a capability of orbiting 40 kg into low Earth orbit. In the second phase, that is the experimental phase, a major exercise was undertaken to create an end-to-end capability in the design, development, and in-orbit management of space systems, together with associated ground systems. These were systems with a limited capability, realized within stringent cost and time controls. In the case of remote sensing, the experimental satellites Bhaskara 1 and Bhaskara 2 were the pioneering steps in this direction. The Bhaskara missions, even with 1 kilometer resolution, enabled developing the capability to image from space, transmitting and processing the image information on the ground, and disseminating the data products to the users. The Ariane passenger payload experiment, known by the acronym APPLE, provided the unique opportunity to design and develop a 3-axis stabilized communication satellite with all relevant technologies with a limited capability of 2 transponders. You know, the modern INSATs carry as much as 30 transponders. Besides building and deploying and in-orbit management of such satellites, a number of interesting communication and broadcasting experiments were carried out with Apple as a forerunner of future operational communication satellites. Even now I remember the Hindu using Apple for facsimile transmission to start new editions in other parts of the country. In the operational phase, major space infrastructure has been created over the last 2 decades. Such infrastructure broadly fall under 2 categories. One for communications, broadcasting, and meteorology, and which is known as the INSAT system. And the second is the space-based remote sensing infrastructure, the Indian remote sensing satellites, the IRS. Of course, I don't have to emphasize the importance of a satellite-based communication and broadcasting system. Sitting at an altitude of, at a height of 36,000 kilometers over the equator, the surface of the Earth, this satellite virtually has an outreach which covers 1/3 of the globe. You have the ability to do point-to-point communications, point to multi-point communication, which is now known as the broadcasting, or multi-point communication to multi-point communications. And one of the other advantages is that satellite is transparent to the ground and undulations, problems of disaster, and many other type of things which can affect the conventional communications. So that's where the importance of the communication systems where we use the space capability. On the other side, if you look at the remote sensing satellite, it provides a synoptic view. For several of the developmental applications, we need to look at it from an altitude so that you get the relation, the spatial relationship between the different features on the ground. This enables you to quantify various types of information, and this kind of quantification, as we will see later, enables us to take an assessment of the resources, their utility, the environmental integrity, and many other aspects. And of course, you can look at several of the dynamic phenomena which no conventional system can enable you to do. Things like looking at the agricultural crop growth or a flooded region, slowly the water receding. This is possible because of the repetitive capability of a satellite system, unlike the conventional ground-based observations. Currently, the INSAT system consists of 6 satellites with a total capacity of 85 transponders providing services for television and telecommunications. The broadcasting capability of these satellites is not only used for regular entertainment, I don't have to say this here to Prasad Bharati representatives, but also for distance education and developmental communications. More recently, these capabilities are being used for newer areas of applications like telemedicine and e-governance. The communication capability of the INSAT system has significantly improved the quality and support of high-density traffic between faraway points and have become a mainstay of the national information infrastructure. At the same time, it has extended the outreach to less accessible areas in the northeast parts of the country and also the downrange islands like the Andaman Nicobar Islands. INSAT has also ushered in a new era of business communications among closed user groups, particularly using the very small aperture terminals, what you call as the VSATs. The INSAT system provides vital information for weather, its 24-hour observation capability of the region, and also provides warnings on cyclones by tracking their movements. Indian Remote Sensing Satellite Program is an excellent example of contribution to societal development and also making forays in the global arena. Based on the experience of the experimental satellites, the Bhaskaras, and taking into account the unique nature of the Indian requirements such as agriculture, the first operational Indian remote sensing satellite was designed and developed over a time frame of 1982-1988. The IRS-1A, launched in 1988, compared favorably in its performance with the then contemporary satellites elsewhere. Within 3 years, an in-orbit spare, the IRS-1B, was launched and together with 1A provided valuable services to the user community. The IRS was the core of an integrated effort to manage the nation's natural resources through a major program, the so-called National Natural Resources Management System, the NNRMS. NNRMS enabled a wide user network through the central and state government agencies in the country to utilize the IRS data and address national development needs in land management, water resources management, environmental and forest inventory, coastal applications, urban and rural applications, and supporting disaster management requirements. Parallelly, through 1990s, the second generation IRS system has been developed with improved capabilities of observation and providing resolution of 5 meters, surpassing the global capability at that time. The unique complement of sensors on the IRS-1C and 1D makes this as one of the most versatile civilian satellites available for Earth observations anywhere in the world. The Earth observer, of course, I should digress here and say a little bit about the way we tried to build this in these three phases. We had this Bhaskaras, which we built in 1979 and 1981. We launched two of them. But then at the end of the Bhaskara, the question was, what is next? There were people who said, well, we have demonstrated it, we have the experience, but there are good satellites available outside, so why don't we use it? But there was a very strong opinion that there is no reason that if somebody could do it, like the Landsat system or the Spot system, the French one, the American one, certainly based on the confidence that we got out of the Bhaskara, we can also build one. That is the genesis of the IRS-1A. We decided that we will as well build something unique in this country. We used very unique technologies. In fact, we wanted to build this satellite so that it can be flown on PSLV. PSLV's capability is limited, so we had to think really innovative to see how we could build a world-class satellite, a satellite comparable to Landsat or Spot, but at the same time capable of being launched with the PSLV. This was a great engineering challenge for the scientists. They did it. By 1988, we had the first of the series, IRS-1A, and when the images came from this satellite, it was incredible. It was comparable to what they get from a Landsat system. But people were not, they were restive. They were not happy with this. They said, if we could build up to this point, why not even better than what others have built? So that was the next step, and that was the genesis of IRS-1C and 1D. They went ahead, they designed and developed very unique optical systems, the like of which you have not seen elsewhere. They made this satellite, they launched it in 1991, 92, in the 90s. And finally, we had these satellites, which became the world's best at that time, a complementary set of sensors, 5 meter, 23 meter, 170 meters, and an extremely unique observation capability. So that is where it stood. And of course, I don't think that the engineers of ISRO, they always feel restless. So they came up with this 1 meter, and 2 weeks back, we launched a 1 meter satellite. So that's the evolution of a capability. That is the evolution of a system. And what is important to note is that it is not that we were trying to look at somebody else's technology. We were trying to look at somebody else's engineering capabilities in building our system. We took our own steps, we took our own directions, and we looked at our own method of doing this, the innovation and so on. The net result is that we have acquired a leadership in this area. And leadership comes because you think original and you do original. If you follow somebody else's ideas and paths, obviously you are not a leader. The development of the Indian remote sensing satellite and Earth observation system is a classic example of how one has to establish leadership in this country. And given the right environment, there's absolutely no doubt that we can be second to none in anything that we undertake. The most complicated science and technology achievements are only an indicator of the overall social transformation that this country can achieve. Of course, the successful launch of the recent TES, the Technology Experimental Satellite, on October 22nd, has given India the capability to produce 1 meter images. Thus, the currently available Indian constellation of IRS satellites are used for land and ocean observations and become the mainstay of the National Natural Resource Management System. IRS satellite systems have also become a part of the global source of remote sensing data and cater significantly to the world market. Now, what is the societal impact of all this? The unique space infrastructure of INSAT and IRS have significant societal and economic contributions. Time may not permit me to cover all the areas, but I would like to provide some important examples of these applications which make India a leading country in space applications too. Let us look at agriculture. Proper estimate of agricultural yields in advance have tremendous impact on our economy as well as social life. Data from IRS has been regularly utilized for assessing the areas under various agriculture crops in various states and also for prediction of their yields about a month in advance of the harvest to the level of accuracies that the Bureau of Economics and Statistics, that is 90% accuracy, 90% confidence level. That's what they demand, and the systems are able to provide that. As a sequel to this experience, an improved model for a national system for forecasting agricultural output from space, agrometeorology, and land based observation, the FASL, FASL, is being instituted by the Ministry of Agriculture in close collaboration with the Department of Space. In past, data from Indian remote sensing satellites have been effectively used for monitoring irrigation commands, for which the country has invested 200,000 crores at the 1996-97 prices in major and medium irrigation projects for faster reclamation of waterlogged and salt-affected lands and developing strategies for micro watershed management, which is key to economic development of rain-fed rural areas, resulting in visible improvement in productivity wherever implemented. Space will continue to be a valuable tool to face the challenges of current times and a future in the field of agriculture, which accounts for nearly 65% of nation's employment and 26% of GDP. Its key challenges in terms of making it profitable for farmers, diversifying it, promoting capital formation, value addition, improving market access, sustaining and improving productivity, all need a sound strategy for its implementation. A vision for an innovative route toward development in agriculture with the backdrop of WTO regime and ecological crisis that threaten to bring down productivity could truly be achieved by the convergence of biotechnology with space and informatics. Precision agriculture embodies such a convergence. With a goal to achieve a quantum jump in agricultural productivity and reduced cost of cultivation, the precision agriculture plays catalytic role in order to achieve a common ground based on convergence of space, bio and information technologies combined with diversified and resilient agricultural systems. Model of precision agriculture has to be adopted to India, taking into account the predominance of fragmented land holdings, heterogeneity of crops and livestock, and concepts of farm families in our rural condition. In the near future, we plan to have a joint program with the Swaminathan Research Foundation, Indian Agricultural Research Institute, Department of Biotechnology, and Department of Space in doing an initial experiment on the precision agriculture. The conceptual basis is being currently worked out. While the ecological integrity of farming system is an imperative need, it's equally important to extend the access of information and market to small farmers. The precision agriculture model for India, while addressing these issues, provides an innovative route for sustainable agriculture in globalized and liberalized economy. At the core of this new emerging agricultural regime will be the dynamic information services emanating from space-based systems which can provide strategies for cropping systems. These strategies can integrate objectives of sustaining productivity of land and water resources, maximizing returns from them, and also effectively responding to external factors such as prices which are influenced by global markets. Such strategies could be implemented with farmers' participation, facilitating aggregated farming so that productivity can still be enhanced, overcoming the disadvantage of fragmented land holdings. Let us look at the water resources. Water is the most important resource that requires proper management and conservation, especially so in a country like India, where there are many regions which face severe shortage as against other regions which are flooded. With around 400 million hectare meter water available annually over the country, only about 12% of the water is efficiently harnessed and used. Strategies to optimize the water use, conservation of the surface and groundwater resources, optimizing the command system, and managing floods are critical. Space has played a major role in this particular area, particularly because of its ability to look at, in a perspective match fashion, several of the features that identify potential water location. IRS images have been the main source of identifying targets of groundwater potential zones, with an early effect to map the hydrogeomorphology of the country at a particular scale. The broad target zones for groundwater were identified and were the basis for further exploration for locating wells and tapping the sources successfully. These groundwater potential maps, prepared using the satellite images, have contributed largely to the success of the National Drinking Water Mission. The targets identified using IRS images have shown great success, even up to 90% in specific areas over the conventional methods, and thus have become an important element of water sourcing. Now, the Ministry of Rural Areas and Employment has launched a major mission to use the IRS images to identify drinking water targets at habitation level. IRS images are used to prepare detailed maps that help in localizing drinking water sources in almost 1.2 lakh habitations in the country in 5 states. These maps are extensively used for locating prospective groundwater sites around the problem habitations. Not only the targeting, but the maps prepared from IRS are also providing information for suitable sites for recharge and thus